Welcome to Spring 2017 weather training for air traffic controllers. This year's module is once again on thunderstorms, and we'll talk about the different types of thunderstorms. We'll review thunderstorm hazards. We'll introduce the Traffic Flow Management Convective Forecast, or TCF, and we'll review some weather radar concerns, including airborne weather radar. First, let's review the thunderstorm characteristics. Now, you know the ingredients needed to produce a thunderstorm. There are three: water vapor, unstable air, which is air that will continue to rise once lifted, and a source of lift, things like a front or heating from the sun, so on. All three of these ingredients are required in order to produce a thunderstorm. If you're missing any one out of the three, you likely will not get the convection necessary to produce a thunderstorm. And there are three stages of a thunderstorm. The first stage is the cumulus stage, where you have the presence of updrafts, the formation of the cloud, but no precipitation yet. There's the mature stage, where the cloud has reached such an altitude that it produces ice crystals in the anvil, and you see the rain shaft underneath. And then there's the dissipating stage, which consists mainly of downdrafts and lingering showers. It's important to note that the ingredients and conditions that produce thunderstorms can change rapidly, so storms may go through all three stages in as little as 30 minutes or last for hours. So it's important to understand what process is at work to forecast how long storms will last, and this has implications for traffic flows. Let's review the different types of thunderstorms. The first type is the single-cell thunderstorm, which consists of a single main updraft that is quickly replaced by a downdraft once precipitation begins. These cells tend to be short-lived, usually just around 30 minutes, and the majority are just sun-driven. They're slow-moving and isolated, so mostly easily avoided by pilots except at night or when embedded. They're sometimes referred to as pulse, popcorn, or air mass thunderstorms in the absence of strong fronts. And these are most frequent during the late summer in the Minneapolis region. The precise locations of this isolated air mass development, like near an airport, are hard to predict. But the takeaway for controllers is that these cells are generally easiest to manage unless they develop directly over an approach segment or airport. The second type of thunderstorm is the multi-cell type of thunderstorm. These refer to the bands or lines that usually occur along a front or an outflow boundary and can last for hours. The individual cells mature and are carried downstream by upper winds. New cells form upwind from the previous cells and take their place. But the cell movement may actually be different than the area or line movement. The cell moves forward, but the area of lift is shifting more slowly. So when someone asks how fast are those thunderstorms moving, you can sometimes give the answer in two different ways: as cell or area or line movement. Kind of an extreme example of this is where you have a training echo situation. The area of lift is not moving or is very, very slowly moving, but the cells within the area are moving along the line or along the area, as they are in this case. This occurs when the lifting process is shifting very slowly, and each of the thunderstorms then follow a path of the preceding storm. The cells move, but the area does not. As you can assume, this will create a large rainfall amount over a short period of time in a small area, which could lead to flash flooding. And depending upon where these thunderstorms set up, it can be extremely tough on air traffic management. On the other hand, when you've got the area of lift shifting very rapidly, like a cold front, thunderstorms may form in a rapidly moving line which can extend laterally for hundreds of miles. These squall lines can persist and move for many hours, even after sundown, and produce damaging winds and hail. Gust fronts, or damaging straight-line winds, are common with these types of storms. And here in Minneapolis, multi-cell squall lines are most common in the spring or early summer, when passing fronts are most intense. The third type of thunderstorm is the supercell thunderstorm, and these are the main sources of severe weather. The updraft speeds are extreme. They can exceed 9,000 feet per minute or 100 miles per hour, and they can be part of a multi-cell cluster or line. But what defines a supercell? The instability and lift is so strong that the cell develops its own rotating mesoscale circulation, sort of like a miniature low-pressure system. And if you observe one of these from a distance, sometimes you can actually see the storm rotating. For controllers, supercells contain the most extreme wind shears, the most extensive turbulence in and around the cells, and they generally have the highest tops of mid-latitude thunderstorms. One thing to keep an eye on is the presence of severe thunderstorm or tornado watches. They are a sign that the development of these conditions is imminent. There's a fourth process that we should be talking about here in the Midwest. There is a source of lift that occurs at night, such that the frequency of thunderstorms is higher than during the daytime for many Great Plains airports such as Omaha and Kansas City. How does this occur? Well, the Midwest has what we call frequent nocturnal activity. This corresponds to the strengthening of the low-level jet over the Great Plains. After sundown, winds increase rapidly from 1,000 to 5,000 feet above the surface and above what we call the nighttime inversion, a layer of warm air above the surface that forms with cooling at the surface. When you get this, low pressure over the Rockies and high pressure exists to the east. This will increase the moist flow over the Gulf of Mexico and up over the plains. This can result in increasing instability and the development of nocturnal thunderstorms, and mostly these will start to the west of Minneapolis over the Dakotas, Nebraska, or Kansas. Sometimes they will develop into an MCS or a mesoscale convective system, which is a large broken area of multiple cells covering hundreds of miles. The low-level jet that produces the thunderstorm actually weakens after sunrise, slowing the moisture transport, and eventually the system weakens. But in the meantime, these systems can produce severe weather and large wind shears at flight altitudes, resulting in moderate to severe turbulence around their periphery, mostly on the north or east sides. Normally, these systems do weaken rapidly after sunrise, but they often foreshadow additional thunderstorm activity in the same region later in the day. Now let's talk a little bit about thunderstorm hazards. These are hazards that can be found with any thunderstorm. They include hail, low-level wind shear, lightning, icing, and turbulence. First, let's look at hail. Hail is associated with sustained updrafts in the front part of a thunderstorm, most frequently with multi-cell or supercell type storms. Controllers should know that damaging hail can often be found aloft, but not necessarily at the surface. It can also be encountered in clear air several miles from thunderstorm clouds, such as under blow-off or anvil tops. And the states with the highest hail risk, with encounters resulting in damage, include western and southern sections of Minneapolis' control space. The second hazard we'd like to look at here is low-level wind shear. Wind shears are abrupt changes in wind direction and or speed, and these can occur at any altitude, but are most dangerous at the surface. A change of wind speed of 10 knots or more at 100 feet in a layer more than 200 feet thick, which occurs within 2,000 feet of the surface, actually defines low-level wind shear. Severe low-level wind shear is defined by an airspeed loss or gain of at least 15 knots and or altitude loss of 500 feet per minute. Wind shear is produced by thunderstorms in two ways. The first way is through a phenomenon called a microburst. Microbursts are downbursts that cover an area of less than 2.5 miles, along a side with peak winds as high as 170 miles an hour that lasts 2 to 5 minutes. It's an area of diverging winds at or near the surface. Once the downdraft hits the surface, impacts the ground, it tends to spread out away from the point of impact. Probably the most important point to remember about microburst shear is that the strong wind shears associated with a microburst are often non-recoverable, meaning there is no piloting technique to survive an encounter, so microburst encounters will frequently result in serious aircraft accidents. The second way that thunderstorms produce significant or hazardous wind shear is through the gust front. A gust front is the leading edge of cool air rushing down and out from a thunderstorm. The edge of the gust front is known as an outflow boundary. The abrupt wind shift in this boundary can actually occur miles away from the parent cell. And here's an example of a gust front being produced by a line of thunderstorms near Grand Forks. You can see the radar has picked up the gust front as an area of a band of weak echo that occurs out ahead of the thunderstorm. It's actually an area of converging winds at or near the surface, contrasting that to the microburst, which is actually an area of diverging winds. The wind shears are usually less critical than the microburst, but note that the parent thunderstorm need not be directly over the airport to affect the safety of approaches or departures. It may be a zone of severe turbulence and cause hazardous landing or departing speed variations. The next hazard we want to look at is lightning. Most lightning strikes do not cause damage. The current is directed along the outside skin of the aircraft. But damage occasionally does occur, and when it does occur, it usually includes outside punctures in the body of the aircraft and damage to the internal electronics or navigational equipment. Significant point to remember here is that airlines must inspect aircraft after a lightning strike, causing flight delays with or without damage, and this can run into significant dollars. Also, aircraft can actually induce lightning strikes. The lack of observed lightning with high-topped echoes may not mean no lightning for a flight approaching a cell. High cells are worth avoiding even without lightning detected. The next hazard is icing. Thunderstorms contain a lot of moisture, and it's abundant supercooled liquid water droplets that form within the thunderstorm that cause the main problem with icing. These occur mostly between 0 degrees and minus 15 degree temperatures within the thunderstorm. These SLDs freeze on impact with an aircraft, and the clear icing accumulation may be very rapid with these types of droplets present. At high levels in a thunderstorm, you can still get icing, but from smaller droplets, and this may be rime or mixed rime, and clear. Virtually any thunderstorm can contain severe icing conditions somewhere in the cloud. Finally, let's look at turbulence. The strongest turbulence with a thunderstorm occurs within the cloud due to shear between the strong updrafts and downdrafts. But severe turbulence associated with a thunderstorm can also occur above, near, and downwind of the cells. Here we have an example of a supercell in the southern plains. Blow-off turbulence occurring in the bordering on the Minneapolis region. And each ride report that we see here reflects a type of turbulence, the green being smooth, yellow being moderate, and the red being severe. You can see that flying through that area, some severe turbulence was reported. In general, pilots are told to avoid the inside of a cell, naturally, but also flying directly above thunderstorms, especially developing cells, and the downwind or blow-off areas. A typical rule of thumb for avoidance distance is about 1 mile away from the storm for every knot of wind at flight level. So if you've got a 60-knot wind at flight level, you want to avoid the downwind area of a thunderstorm by at least 60 nautical miles. On other sides, the area you want to avoid is within 5 miles of a cell, sometimes a greater distance depending upon altitude and the pyreps. A minimum 20 nautical miles is often recommended when you get above flight level 200 or around heavy cells on radar. Now let's look at a new product that we're using in the National Telcon to come up with traffic programs. It's called the TCF. The TCF in this case is not a bank. It stands for Traffic Flow Management Convective Forecast. It looks and feels like the old CCFP. It is a collaborative product between AWC, CWSUs, and private industry forecasters, but it has some exceptions, differences between it and the old CCFP. Let's take a look at some of these differences. Compare this year's product with last year's Thunderstorm suite of products. Last year we were using the CAUS and the CCFP. These two products have been discontinued. The TCF, which has taken their place, is a single product. It's issued 24/7, every 2 hours. It has 3 panels for a 4, 6 to 8 hour forecast. The 2-hour forecast is no longer available. And probably the most important difference to make note of is that only high confidence areas are portrayed on the TCF. Low confidence areas are not plotted. It is available through the TSD and online, and it is a graphic only product. There is no text associated with it. The TCF will cover all the domestic US FIRs, and in Canada, when the Canadians are participating in the production of the TCF, their area will cover an area south of the line from Thunder Bay, Ontario to Quebec City, Quebec. Their participation will run from April 1st till September 30th. There is a minimum criteria for an area of convection to be included in the TCF. You must have composite radar reflectivity of at least 40 dBz. The echo tops must be at or above flight level 25,000 feet, and the coverage of those two features must reach at least 25% of the polygon area. Finally, you do have to have high confidence that these criteria, A, B, and C, will be met. For lines of convection in the TCF, it's the same criteria for reflectivity and also echo tops, but the line must have at least a coverage of 40% or greater. And the key is very similar to what the CCFP had. You've got light blue lines, some moderate shading for sparse coverage, and solid hatching for medium coverage. And again, the confidence is always plotted as blue, meaning high confidence. And there are 2 different types of lines, either broken, 40 to 74% coverage, and then solid, between 75 and 100% coverage. And the lines can stand alone or be included or embedded within areas. The number that you see associated with each area is the height of the maximum echo tops in that area. And here are some examples. You can see it looks very similar to the old CCFP. It's labeled, each area labeled with height of the echo tops, and the shading or the broken or solid nature of the line coverage indicates the coverage of that area of thunderstorms. We've already started producing this product. It began on the 1st of March. It will end, the season will end on the 31st of October, and the Canadian participation will be between April 1st and the 30th of September. Now let's turn to weather radar issues and focus first on false echoes. There are some common issues with any weather radar. There's three basic ones: ground clutter, anomalous propagation, or AP, and attenuation. It's important to remember that WARP uses the National Weather Service NEXRAD radar network. And NEXRAD does eliminate stationary ground clutter patterns, except wind farm signatures. And we'll talk a little bit more about those here in a minute. Anomalous propagation, or AP, is still frequently an issue, and this is a case where the radar beam is refracted due to temperature inversions. You see this most frequently during summer evenings as an inversion develops, and the pattern and intensities in AP are random. And it's how you can tell the difference between AP and real-time cells. These echoes that you see here are not contoured. Attenuation is where some radar energy is absorbed by detected objects. The warp system that you're using uses mosaic displays, which combine multiple radar sites, so this eliminates a lot of the attenuation issues found with a single site radar. Now, airborne radar acts more like a single site radar, single site ground radar, but there are some differences. It's not necessarily better than ground-based, it's just different. Controllers can assist pilots with their ground-based radar displays, so you should be aware of some limitations of airborne radar. Never assume that airborne radar is more accurate. First, let's talk about reflectivity. Reflectivity on any radar is determined by the size of the particles, and also by the wetness or dryness of particles. Wet particles are much more reflective. One important point to remember is NEXRAD, or the radar used by WARP, is far more sensitive to dry particles than airborne radar. So when you have a situation where you have wet hail, the airborne radar will pick that up much more easily than what you would receive from dry hail. Rain, wet snow, and sleet are also more reflective than ice crystals and dry snow. So thunderstorm tops that are comprised primarily of ice crystals are not going to be seen well on airborne radar. They are detected by the ground-based NEXRAD radar much better than a airborne radar. There are also some limits due to attenuation with airborne radar. Many times the airborne radar energy is not able to make it all the way through the closest echo. So the cells that are present behind the front echo do not appear. Because you are looking at a mosaic, you will often see a more realistic picture of all echoes in an area than a pilot will on their small single-site radar. There are also some limitations due to antenna tilt. Pilots do have control over the tilt of their radar antenna to above or below the horizon by as much as 15 degrees. But there are some inherent problems with this. This can cause overlooking and underestimating echo intensity. Your warp radar mosaic includes more levels over distance and will give a more complete vertical picture than a single aircraft radar. In this case, all a pilot would have to do is tilt the radar down by 2 degrees and then see much more significant top information. Then there's some limitations related to range. Most airborne radars have a useful range of 80 miles, but pilots may be using a shorter setting. NEXRAD ranges from 143 to 286 miles depending upon mode. And you also have those overlapping radars in the mosaics used by WARP. So that eliminates a lot of the range issues. Here we have a route selection that may adversely be affected by the choice of radar range. For example, a pilot has his range selected at 40 miles. He sees a path through that. It is open without any thunderstorm activity, but he can only see out as far as 40 miles. Had his radar been set at the 80-mile range, he would see that beyond the limit of his radar, there is a large cell. So judgment can be sometimes impaired by the choice of range, and a controller would be able to provide valuable input. There's also some issues with volcanic ash related to radar. Volcanic ash does not show up on airborne radar. And it's also important to note that ground-based radar detection is not reliable. The best way to track volcanic ash plumes is to use dispersion models and trajectory forecasts in conjunction with satellite observations. Pilot observations may not always be reliable sources because volcanic ash plumes can look like ordinary weather clouds. Finally, let's take a look at wind farm interference. It's a problem in the Midwest because of the increase of these locations. The spinning turbine blades inhibit the radar's ability to filter turbine echoes. The radar algorithms actually respond to moving targets, so the resulting echoes look just like storms or severe weather on radar. They may actually be contoured, unlike the AP echoes that you normally see. Turbines can also cause partial beam blockage and shadow effects if located within 18 kilometers of the radar site. We're still trying to come up with mitigation techniques, but it may be impossible to eliminate all the effects of wind farm interference. The best form of mitigation remains to keep wind turbines out of the radar line of sight, but often this is not practical. So it's important to know where wind farms are located. It's important to note that the echo does not move. You need to compare the echo that you're seeing with surrounding echoes. And the fact is that these are often not seen in the absence of AP producing inversions if the wind farms, as in the Minneapolis case, are far enough away. If you have AP, you may see wind farm echoes. If you don't, chances are you will also avoid that interference. Other NEXRAD sites in the Minneapolis area may actually be closer to wind farms than Minneapolis radar and more vulnerable to interference. And here are some examples. You can see this is a map of the wind farm locations within our area. There's a heavy concentration of wind farms to our south over southern Minnesota and Iowa, but you do have a number of wind farms in other places around the ZMP that are close to weather radar. So these are some typical radar signatures produced by the wind farms in each of these areas. That's it for this year's 2017 Thunderstorm module. Thanks again for your attention.